The midspan section of a simply supported girder of span 8 meter is a symmetrical I section, 250 by 500 mm overall. The flanges are 100 mm thick and the web is 80 mm thick. The girder carries a UDL live load of 10 kN per meter. Determine the initial pre-stressing force and its eccentricity so that no tension is allowed in concrete both at transfer and service load. Loss of pre-stress is 18%. Take the density of concrete as 25 kilonewton per meter cube. So from the data, we have to draw the sketch very clearly and carefully. Drawing the sketch is the integral part in solving the problems in the pre-stressed concrete. So let us quickly draw the sketch. And the overall dimension is 250 by 500. So width, this is 250 and this is referred to as 500. So flange dimension is given as 250 by 100 mm. Web is 800 and bottom flange is referred to, it is a symmetrical section, so it can be taken equal. Flanges are equal, and this is how the cross section looks like. And here on the right hand side we need to draw the simply supported beam which carries uniformly distributed load. It is carrying the load of 10 kilonewton per meter and the span is 8 meter. The most important part in this question is that we need to read this statement carefully. No tension is allowed in the concrete both at transfer and service load, and here it is been noted down. Given no tension is allowed at surface transfer as well as the working condition, this is one of the important conditions specified. This has to be kept in mind before solving. And next, immediately after drafting the sketch, so it is required to compute the area of the cross sectional area of the beam. So since it is a I section, so easily it can be calculated. We have two number of the equal flange 1, flange 2. Therefore, it is 2 number. Flange dimension is 200 and 500 and plus 80. So, after deducting flange thickness 100, 500 minus 200, it comes out to be 300. And that is how the final answer is obtained. And next, we need to find out what is the moment of inertia about the neutral axis. This is the neutral axis. So, there are several methods to find out the moment of inertia. So let us solve it here it in a simplified manner. See here, since it is a symmetrical section, I am just considering this I section as completely whole of a triangle. So I am just taking it as a rectangle. I'm just taking it as a rectangle. So from this rectangle, I'm just trying to deduct these smaller two rectangles. These smaller rectangle which is been highlighted in red color. Okay. And it can be noticed here in the sketch. It is shown that 250 by 500 cube divided by 12 is nothing but the moment of inertia of the whole rectangle, minus 2 into 2 is nothing but there are two number of the rectangles. This is one rectangle, this is one smaller rectangle. So if we deduct these two rectangle by calculating it suitably, we can easily obtain the moment of inertia. So final moment of inertia is 2.22 into 10 power 9. And next, it is necessary to compute what is known as section modulus. As I have told several times, section modulus can be easily computed as I by y. Substituting all the values, since it is a symmetrical section, the overall depth is 500 divided by 2. The depth of neutral axis is 250. And let us calculate what is the dead load, that is self weight of the beam. It is designated as Wg. It is area into density. Area is previously calculated density. And since it is a simply supported beam carrying UDL, the bending moment at the central span is given by WL square by 8. Accordingly, the substitution needs to be done. And next, the most important condition is here. First condition is that at transfer condition. So whenever the process of pre-stressing is happening, the concrete member will not be subjected to any kind of the external actions. So during that phase, that is during transfer condition, only the pre-stress condition and the self weight has to be considered here. This is very important. So I'll just draw a one example. So let us say that we are trying to pre-stress a concrete beam. We are trying to produce or manufacture a concrete beam. So what happens? So we are introducing the steel, that is tendon here. As soon as we start tensioning, we are trying to pull it from both the ends. As a result of the internal resistance, they set up the resistance to the external action. As a result of it, this beams tends to bend in the upward direction. So that is, tension will be acted in the upward direction, compression will be acted in the downward direction. So this is what the sketch which is written here. I repeat, whenever we are trying to pre-stress a concrete beam, we are trying to pull it from both the ends. As a result of the internal resistance, the pushing action will be generated in the tendon. Due to that pushing action, this beam tries to bend in the upward direction, and this is being designated here in this fashion. I hope this is clear. And then no tension means tension, one more important condition means given no tension, which means no tension means it has to be equated to 0. This condition is very important. No tension means it has to be equated to 0. See, which is the expression it is being considered here? F superior. Then where the tension is acting here? Tension is acting in the upside, that is upwards. So therefore we have chosen F superior equation, since no tension means it has to be equated to 0. So why it has been F superior here? F superior has been considered because the tension is acting in the top fiber. Top fiber resultant stress equation is given by F superior, and therefore it has to be equated to 0. After substituting, we will get an expression in the format of P and PE. So next, let us proceed to the second condition. So second condition is that at the service condition or the working condition. So what happens in the case of the service condition? So let us see that. So as I have told, in the case concrete beam, when we start pre-stressing, pulling, we start subjecting it to pulling. As a result of internal resistance, this starts tends to pushing. So because of this action and reaction, this beam tries to bend in the upward direction, that is during the transfer condition. So here in preliminary phase, tension will be acting upward, compression will be acting in the bottom fiber, and here in the working condition means you are subjecting it to loading condition. You are trying to apply the loads externally. As a result of applying the loads externally, what happens? Due to the application of the load like this beam tends to bend in this fashion, which means tension gets shifted here at the bottom fiber and compression shifted to the top fiber, that is C, and that is what the sketch which is being written here in the left side, which means at the bottom fiber tension is acting, compression is acting at the top fiber, as a result of which, so here the F inferior, since the tension is acting here, since the tension is acting here, we need to choose the F inferior equation and then equate it into 0. So see, the one more major condition I have specified in the beginning, no tension is allowed in the working condition, which means tension is totally 0. See, the fundamental aim of the pre-stressed concrete is to nullify the tension. Okay, so and during both the transfer condition as well as the working condition, tension is totally 0, and where the tension is acting, relevant expression has to be chosen, that is we have chosen here F inferior. Okay, the problem hint has to be analyzed very carefully, and the suitable expressions has to be taken care. And next, in addition to it, the loss of pre-stress has to be considered only in the working condition. See, during the process of pre-stressing, losses are generally not expected because still you are pre-stressing. Okay, still you are pre-stressing the beam, you are only just trying to pre-stress the beam. During the phase of transferring the pre-stress, loss is generally not expected here. So when you are going to expect the loss is expected only when the complete process of pre-stressing is done, it is completed. Post pre-stressing only loss is expected. The loss percentage given in the problem, it is 18%, I think. But out of 100% of the pre-stressing, if 18% is getting lost, what is the remaining amount? Remaining amount is generally calculated as 100 minus 18, it is nothing but 82. Most of the time we are taking it as a loss ratio divided by 100, and it is obtained as 0.82. Fine. So you have to multiply that only for the P. Wherever the pre-stressing P is available, that is only at the phase, that is pre-stress due to the direct stress due to the pre-stressing and pre-stress due to the bending. Only in these two cases the losses has to be multiplied, whereas in these two cases, dead load and live load case, the losses should not be accounted. So this is also one of the major thing to be accounted while solving the problem. And next, one more equations will be obtained after solving everything. See, here we have to note down P and P expressions. So after you solve for everything in the calculator, simultaneous equations can be solved. You will get the values in the calculator for P and PE. So one value you get for P, one x value you get for PE. So this P you will get it as direct value. You can substitute that P value here and substitute E, and then find out, and you can take the P value, and here there will be one more value from the calculator. E can be determined easily. And finally the obtained P value is 421, eccentricity is 154 mm.